Heisenberg's uncertainty principle. According to de Broglie dual nature theory, every moving particle, be it an electron, proton, etc., is associated with a wave nature. Such waves are known as matter waves. So, for a particle moving in a one-dimensional space, for example, along the x-axis, the wave function can be represented by the sinusoidal function as shown. If the position of the particle is well defined, that is, its position can be known exactly, then its wave function is a sharply peaked function, where the amplitude A is represented on the y-axis. It is important to note that the wave function has zero amplitude everywhere else, except at the location of the particle. It is also important to remember that each wave function represents a component of different momentums for the particle in one-dimensional space considered, that is, along the x-axis. Now, if we consider a number of such wave functions, each with a different de Broglie wavelength superposing the other, it results in wave function as shown. It is clear that the superposed wave function does not have a well-defined peak. Rather, it represents the approximate position of the particle. Therefore, we can say that there is some uncertainty, say delta x, in the location of the particle. Thus, for a finite uncertainty in the position delta x, we see that the wave function is built up of separate wavelengths spread around the central wavelength. If we now look at the superimposition of increased number of wave functions representing various components of different momentums of the particle, then the superposed wave function has a peak sharper than before. This means that the uncertainty in the position of the particle delta x has decreased compared to the previous case. Thus, as we go on increasing the number of superimposing wave functions, which represents the components of different momentums of the particle, we see the single wave function obtained by their superimposition, resulting in a narrow peak. Thus, the uncertainty in the position of the particle reduces. When infinite wave functions representing different components of momentums of the particle are superimposed, we get a single wave function, which has a very sharp peak. Thus, the uncertainty in the position of the particle is reduced to zero, and thus we can locate the position of particle with maximum possible accuracy. When the uncertainty in the position of the particle is zero, we say that we have localized the particle. But for this, we use infinite number of wave functions representing the components of different momentums of the particle. In this process, we lost all information regarding the momentum of particle. Thus, the uncertainty delta p in the determination of the exact momentum of the particle is now infinity. From this discussion, it is clear that the exact position and momentum of a particle cannot be determined simultaneously. This is the essence of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that it is not possible to simultaneously measure the position and the momentum of a particle exactly. If delta x and delta p represent the u certainty in a position and momentum of a particle, then, according to the uncertainty principle, delta x or delta p is greater than or equal to h cross by 2. Since h cross is equal to h by 2 pi, we have delta x or delta p greater than or equal to h by 4 pi, where h is the Planck's constant. Let this be equation 1. Rearranging the terms in equation 1, we see that greater the value of delta x, smaller will be the value of delta p, and vice versa. If delta p is equal to 0, that is, when the uncertainty in the momentum of the particle is 0, then the uncertainty in the position of the particle becomes infinity. That is, it is impossible to exactly determine the position of the particle. This implies that we don't have an exact idea about the position of the particle. Similarly, if delta x is equal to 0, then delta p is infinity. That is, if the uncertainty in position of the particle is illuminated, we cannot determine its exact momentum. To understand the uncertainty principle better, let us consider a projectile of mass 1 gram, that is 10 power minus 3 kg, moving such that the uncertainty in its velocity, delta v, is equal to 10 to the power of minus 6 meter per second. Then, the uncertainty in its momentum, delta p, will be equal to m delta v. Then, the minimum uncertainty in the position of the particle is delta x is equal to h by m delta v into 4 pi. Substituting the values of the variables involved and solving, we get delta x very negligible, and hence the uncertainty in the position of microscopic objects around us is very difficult to visualize. For the same uncertainty in the velocity, if we consider an electron, then substituting the mass of electron m, which is equal to 9.1 into 10 power minus 31 kg, we get the minimum uncertainty in the position delta x for the electron, which is very huge and far greater than the size of the atom. Thus, for subatomic particles, the uncertainty in the position is very high. Hence, we can say that the uncertainty principle has a larger importance in the context of the subatomic world.